Welcome in this video where we're going to implement the great K-planes paper. That's a great paper that works both for static scene and dynamic scene, and that is pretty fast and allows rendering in real time. So these are the results we'll get by the end of this video. So yeah, pretty great results with an implementation in about 100 lines of code. There are a few improvements we can make to implementation. I will, when they appear, I will give you pointers to them and give you a suggestion of what you could do to improve the implementation. But this is already quite great. I will put a link of this source code in the description. If you find the code useful, please leave a star. It's always helpful. Also leave a thumbs up to this video and subscribe for more content related to NeRF. That being said, let's dive into the implementation. So as usual in this channel, we'll use PyTorch to implement everything related to the neural networks, and we'll also use NumPy for implementing a few helpers. So we can start by implementing our NeRF model. So for the position, there are no more positional encoding, because now the features for the position are encoded in those planes, in those K planes. But for the direction will be directly fed to a MLP, to a neural network. So we need to do positional encoding for the direction, and therefore we need to take as input the dimension for the positional encoding of the direction. We can also take the hidden dimension of the neural network. So you can see that this approach is a bit similar to instant and GP. We now try to encode as much information as possible in data structures such as K-planes, and then with a tiny MLP that is very small that will do the remaining of the work. We take n as input, which is the resolution of the K-planes. So the resolution, there will be 512 by 512 each of those planes. In this video we are working on static scenes, so we will have 3 planes. And then we can have f, which is equal to 96. It's the number of features that are stored by each plane. On scale, so that means that when we have a look at this grid, we need to mention what is the size let's say for example in meters of the side of this grid. And in our case we are working with 1.5 times 1.5 meters. That means that we suggest that our object is in a bounding box of scale 1.5 meter. Both side is 1.5 meter. So let's say you have objects that are a bit bigger, you will need to play with this hyperparameter to adjust for the scale of the object. Okay, so let's start to implement our K-planes. So we can implement the XY plane, the YZ plane, and the XZ plane. So there are 3 planes. Let's say that you want to work with dynamic models, then you would have 6 planes: XY, YZ, XZ, and then XT, YT, ZT. So we disentangle all the coordinates. So we create a grid of size. So this grid, the size is n by n, and then for in each cell we store f features. Then we can implement the neural network. So very tiny neural network. We start with f, which is the features, 96 features. Then the hidden dimension is pretty small, 64. Then there's a standard MLP with a redo activation function. Then we map this to 16 values. So out of those 16 values, 15 will be kept. So 15 will be kept as hidden features, while 1 value will be extracted and will be the density. And then to the second block, we feed those 15 features extracted from the first block, and then we add additional values. Those will be the embedded direction. So for the direction, we do what we could do is instead of 4 there, we should use embedded dim direction. Here the value 4 is hard-coded, but basically if we are using positional encoding and using a dimension of 4, there will be 3, which is the size of the dimension of the direction, times 4, times 2, because we are using for each component we are using the sine and the cosine. So we are using we encoded with 2 values, and then plus 3 because we concatenate the direction to the positional encoding. Maybe that does not make so much sense, so that will make more sense when we move on to the positional encoding. But basically a standard MLP that is very similar to what is done with NeRF. First we have a first block that just takes the position as input, that predicts the density, and then we have the tail of the neural network that predicts the color, and that is direction dependent. Okay, now we can move to positional encoding. So this is what I was saying. If L is equal to 4, then for each component, we compute the sine and the cosine of x. The size of x is 3. So we have 2 times 3 times L component. So 3 times 2 times L, where L is the embedding dimension, which is 4 in our case. And then plus 3, because we keep x in the positional encoding. So we concatenate the initial direction to the embedded direction. Okay, now we can implement the forward function. So first we prepare the tensors that will store the density and the color. So by default we set them to 0. And then we can create a mask. So we need to check for each point that are queried, for each point that we need to give the density of and the color of, we need to make sure that they are within the bounding box represented by the k-planes. And then we can compute the index in which the cells in which those points will fall. And then we can query the k-planes using those indices that we've computed. Yeah, so basically we are just querying the features at the appropriate locations. If you want to improve the code, what you can do is to add bilinear interpolation, which I've not done. So by using bilinear interpolation, you should get smoother results. It should make the impression that the resolution is increased. That's very simple to do. You can use the function f.bilinear from PyTorch. You can do that as a homework. Let's say you are interested in doing it. You can also, you can of course make a pull request if you're interested. Yeah, so just try to do it as a homework, and let's see what you get. So once you've extracted the features for each plane, and then in the paper they explain why the Hartman product is interesting, why it's why they chose to do the Hartman product rather than something else. So basically, to compute the final features, we do an element-wise multiplication between the features of each plane. And when this is done, we can finally smear those features to the neural network. So first to the first block to get the hidden features. Then we extract the density from those hidden features, and then we predict the color for with the last block, and we give the direction as input, and we do positional encoding of the direction. And you see we have this mask. So the mask says the mask only keep points that are within the volume. We only predict colors and density for points that are within the volume. For others, we just keep the color and density to 0. It's important to compute this mask, otherwise we would have index out of bounds. Okay, so now we've pretty much implemented the k-planes paper. Now everything else is just a standard NeRF implementation. For example, our testing function that will take a dataset, an index in the dataset, and we will render the image at that index. So the first thing we do is to get the origin and direction for that image. And then because if we try to, even though k-planes is using much less memory than vanilla NeRF, if we try to render all the image at the same time, we will have CUDA out of memory. So we render the image chunk by chunk. So basically we're doing batching. So we are doing array per array, batch per batch. And then we form the final image by concatenating all the pixels we've accumulated so far. And then we can just plot the figure. Okay, great. So now we can compute the accumulated transmittance. Computing the accumulated transmittance is pretty straightforward. It's a straightforward implementation of the equation from the initial NeRF paper that is repeated in most paper. Yeah, I will not spend much time on that, just an implementation of the equation. As always, I do not spend time on the equation, I really focus on the implementation, but I just remind you that I have a course on Udemy about NeRF in case you are interested and want to learn more about the maths behind it. Okay, then there is the rendering function. We take as input a model. This is standard in rendering. We always start with a 3D model. In this case, the model is represented by a NeRF, by a neural network, but in standard ray tracing software such as Blender, such as Unreal Engine, your model is your 3D mesh, basically. So we take a model of the 3D scene, we take the origin and direction of some rays, so we take rays as input, the near and far plane, and then the number of bins to do the quadrature. So first we sample T, we sample we sample time t at which we need to evaluate the rays. Then we do perturb sampling along those points that are sampled. So we perturb them, we add some noise to them, so that we are not always sampling at the same time t. Otherwise, that will lead to overfitting. We will sample always the same points in 3D, and that will lead to overfitting. We also compute delta, so the distance between two successive time t, that will be useful to compute the quadrature. So once we have t, we have sample t, we can use them to compute points in 3D space. So we just use the equation of array to compute its position at time t. And then we can reshape the direction so that the direction will have the same shape as the point x, and so that we have pairs. So for each point x there is a direction, and we can send that to the neural network to get the colors and density of those point x with those directions. Once we have the colors and the density, we can finally compute the rendering integral. That is well explained in the NeRF paper or in any follow-up paper. So we are just computing the volumetric rendering integral, and we are also doing a white background regularization. I explained that in the previous video in more detail. I will also explain that in my course, so I will not spend time on that. But because our background is white, we add those two terms. This is a regularization for synthetic data with white backgrounds. Okay, now we can implement the training function. As I like to say, it's just supervised learning with the ground truth values that are the ground truth pixel values, and then we ask the neural network to make a prediction, and then we do a regression between the predicted value and between the predicted value and the rendered value, and we do a gradient step on that. So we iterate over our data loader, we get the origin, direction, and ground truth pixel values, and then based on the ray origin and ray direction, we can regenerate a new pixel values. We can do rendering by querying the NeRF model at those for those rays, and then we can compute the MSE loss between the prediction and the ground truth. And then we do one gradient step, which is easily done in PyTorch. If we have a scheduler, we can do a scheduler step. This is pretty common with NeRF to reduce the learning rate over time, and we can return the training loss after training. And finally, we can put all the components together. We will train on a GPU that will be much faster, of course. We can load our training data. So usually in my videos, I do not spend time on generating the data set, so that we can just focus on what is important. If you are interested in understanding all the data set was generated, again, you may be interested in my course. But otherwise, I think everything here is self-contained. So once we've loaded the data, we can create a NeRF model, we can create an optimizer, a scheduler, and then finally we can create a data loader, basically just transforming the training data set into a PyTorch data loader, and call the training function to train everything. And when this is done, we can call the testing function for each test image to do a rendering. And you will see that if you go back to my first video about NeRF, so vanilla NeRF, this was very slow to do the rendering, and K-planes like for example instant NGP are very fast, and this is very enjoyable. This for loop is very fast. So that's it for this video. I really hope you liked it. Again, please, if it was the case, leave a thumbs up. Do not forget to subscribe for more content related to NeRF, and thank you for having followed this video.